Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our class 12th physics playlist, we will study one important board exam topic of nuclear physics, that is atomic mass unit, and we'll also learn one atomic mass unit is equivalent to 931 million electron volt energy. So let's start study of atomic mass unit. Let's first understand the significance of atomic mass unit in nuclear physics studies. As per special theory of relativity given by Albert Einstein, both mass and energy are different manifestation of the same thing. The same thing is represented in two different formats, mass and energy. According to Einstein relativity theory, mass is a condensed form of energy. Hence, mass and energy can be mutually transformed from one form to the another in nuclear actions, and the conversion of mass and energy is governed by mass energy conversion relation equal to mc square, where E is energy of action in joule, mass here is in mks kg unit, and c is velocity of light 3 into 10 to the power 8 meter per second. And in nuclear physics, both mass and energy are usually expressed by atomic mass unit or AMU, abbreviated as only U. As per definition, one atomic mass unit or one AMU is 1/12, 1/12th part of rest mass of carbon 12 atom, which is the most abundant and most stable form of carbon. Now the carbon 12 atom consists of nucleus having 6 proton and 6 neutron and 6 orbital electrons. Now these electrons have negligible mass, so we can say the total mass of carbon 12 atom is 12 AMU. Numerically, one carbon 12 atom got 1.996 into 10 to the power minus 26 kg mass, and its 1/12th part is one atomic mass unit. So one AMU is approximately equal to 1.66 into 10 to the power minus 27 kilogram. So one carbon 12 rest mass is 12 AMU, and one AMU is 1/12th part of carbon 12 atom mass. In nuclear physics, in reaction, when mass or mass defect is given in AMU, then energy produced by that mass is equivalently obtained by E equal to mc square relation, and 1 AMU energy is equivalent to its mass in kg, 1.66 into 10 to the power minus 27 kg, multiplied by square of velocity of light 3 into 10 to the power 8, and when this is simplified in joule, this energy comes as 1.5 into 10 to the power minus 10. So 1 AMU is 1.5 into 10 to the power minus 10 joule. Now this joule energy can be converted in EV by division of electronic charge, and when joule energy is converted into EV, it comes as 931 into 10 to the power 6 EV or 931 million EV. So 1 AMU mass is equivalent to 931 million EV energy, or 930 million EV energy is equivalent to 1 AMU mass. The two numerical example will explain the concept of mass energy equivalency in an atomic reactor for electricity generation. When uranium is used, its 0.09% part of mass get converted into heat energy, and that heat produce steam to run a steam turbine, and mechanical energy of steam turbine is used to generate electrical energy in a coupled electric generator. Now this reactor got a electrical power capacity of 500 megawatt, and the combined efficiency of the process is 30%. That means out of total heat produced in reactor, the 30% of that heat get converted into electrical power output. We have to find out the amount of uranium that will be consumed in reactor per day when the reactor is operating at its rated 500 megawatt power capacity. Let's assume that this plant use m kg of uranium daily for its rated operation, and since only 0.09%, so percentage value 0.09% is converted into per unit by division of 100, and this much part of total mass m in kg when multiplied with square of light velocity 3 into 10 to the power 8 square. This energy in joule comes as 8.1 m into 10 to the power 13 joule, where m is mass of uranium used per day in reactor in kg. Now the daily consumption of uranium mass m can be calculated by equivalency of power output with heat input. Now the power output of plant is 500 megawatt. In watt it is 500 into 10 to the power 6 watt. Now the overall efficiency of plant is 30%. So the input heat for reactor is output divided by overall efficiency. Now this watt heat power in 24 hours and 1 hour got 3600 second become watt second energy or joule energy 1.44 into 10 to the power 14 joule. So 1.44 into 10 to the power 14 heat energy of reactor is produced by m kg of mass, and m kg mass produce 8.1 into 10 to the power 13 into m joule energy. So when two energy of mass and electrical output divided by efficiency are equated, the mass of uranium used daily in reactor can be obtained as, now the power 10 to the power 13 and 14 are matched by making multiplication of 10 with 1.44, and this is 14.4 into 10 to the power 13. 10 to the power 13 will get cancelled out. So the mass in kg is 14.4 divided by 8.1, and it is just 1.8 kg. It means only 1.8 kg of uranium mass is sufficient to produce 500 megawatt electrical output in this reactor for a day. So a very small amount of mass can produce huge amount of energy, as mass is a very condensed form of energy as per E equal to mc square relation. This example is a great piece to explain the concept. In a fission process of uranium-235 nuclei, the mass defect per fission process is just 0.2 AMU. That means when a fission of one uranium-235 nuclide takes place, in the complete process 0.2 AMU mass get converted into energy. We have to find out how much amount of uranium will be consumed in that nuclear reactor, which produce 100 megawatt power for 1 hour. Now the overall efficiency of this plant is 40%. So we can find out energy produced by reactor in 1 hour at 100 megawatt power and 40% overall efficiency. This is heat energy produced in watt for 1 hour, 3600 second. So watt into second is the joule energy produced by reactor in 1 hour, equal to 9 into 10 to the power 11 joule. Now energy of per fission process of uranium-235 nuclei is 0.2 AMU, and 1 AMU is equal to 931 million electron volt. 1 EV can be converted into joule by multiplication of electronic charge 1.6 into 10 to the power minus 19, and one fission process will produce 2.98 into 10 to the power minus 11 joule energy. So we can find out number of required fission in 1 hour, and it is a ratio of energy of 1 hour divided by energy of one fission process, and total energy of 1 hour is 9 into 10 to the power 11 joule, and energy of one fission process is 2.98 into 10 to the power minus 11. It means in all roughly we need 3 into 10 to the power 22 number of fission in an hour to produce 100 megawatt power output. Now the mass of uranium-235 can be obtained by the concept of Avogadro. In 1 mole of uranium having 6 into 10 to the power 23 species, the mass of uranium is 235 gram. So if the fission of 3 into 10 to the power 22 uranium atom is there, then 3 into 10 to the power 22 atoms will have total mass 235 gram divided by Avogadro number into number of fission, and it is just 11.7 gram. So just 11.7 gram of uranium mass produce 100 megawatt power for 1 hour. Again it amplify that a very small amount of mass defect can produce enormous amount of energy output, as mass is very condensed form of energy. We hope you now understand the concept of atomic mass unit, and also understand how mass and energy equivalency calculations E equal to mc square is done, and practice of numerical will enhance your subject clarity and exam success. our other learning video of the same playlist are equally useful, and you can also join our online doubt clearing classes and can use our exam centric notes by joining our YouTube channel membership by just clicking join button just beneath. Have a nice time. Thank you very much.